I have one choose no. Okay, so let's start the pool over there. So 9.99, if it is acceptable or not, it depends on if it is below, I mean, the range or not. So it's between the 9.95 to 10.05, so it's good. Anything like above it or below it, it will not acceptable. Okay, so this is about the tolerance stuffs over there. Now let's talk about how to do it. So any process, because we like to answer if it is capable. So we find this is the upper limits, this is the lower limits, and the green line here is what we call the real distribution. And how can we get that distribution? Because we compute the sigma. So we compute the standard deviation. And then we have that distribution looks like this. Okay. So for any distribution, because it comes for the data you connect, this is the real data. This is the real length for each apple pen you produced. Then we connect all the data, we compute the standard deviation for all the length you connect. Then we have this distribution, it looks like this. And any distribution, if it is between, if it is within the limits, then it means the process is capable. And for any distribution, if it is something outside the limits, which means above the upper or below the lower, then it's not capable. So this is how we get that ideas, if it's capable or not. Then back to the process capability, how to do it. We just need to compare these two things. We need to compare what is your real, which one we call the actual. What is your actual number? What is your actual distribution? What is your actual sigma? And your specification limits, because the upper lower comes for your specification. So we consider the specification as well. We just compare these two things. And we use specification divided by actual. This is what we have for CP, the process capability ratio. So this is how we compute that. Okay. Okay, here we go. So CP equal to the acceptable, which is your specification, divided by actual, which is your distribution. So the acceptable, we use the limits differences. And the actual, we consider the sigma, which is the standard deviation, is the distribution over there. So the CP equals to, we consider, because we consider all the positive numbers, so we take the absolute value into consideration. So we use the upper limits minus the lower limits and divided by 6. 6 is a constant. 6 sigma. Sigma here is your standard deviation. It's your process variabilities. And we use the specification you design divided by the actual numbers you connect. Then we got the process over there. So how it is, if your process capable or not capable, we consider the result of CP. If CP larger than 1, it means your process is capable. If less than 1, it means no. If equal to 1, it's just within. This is what we have. Why? So take a look at the figures here. If your CP is larger than 1, which means this one. This is your specification. Should be larger than the real distribution. So this is your specification limits. And it's larger than the distribution. So the distribution will less than the range, the limits. So if larger, it will look like this. So it's capable. Your process is good. But if the limits less than the real distribution, the CP result will be less than number one. So it will look like this. So it's not capable. Okay. So there are two things. First of all, you need to figure out how to compute CP. It equals to the differences between the specification limits divided by 6 times the sigma. Sigma is your standard deviation. And the second thing you need to figure out is how you can get the conclusions for the CP. You will get a result of CP, but how is it, how the process is capable or not? Then you need to compare the CP with number 1. If larger than number 1, it's good. If less than number 1, not good. Okay? Any questions here? If no, let's consider. Let's talk about. I just gave you like numbers over there and think about if it's capable or not. So how about you calculate CP and it's equal to 1.33 if it is capable or not capable? No? Yes, yes, yes. Now I have 4 years, 5 years, 1 no, 6 years. 7 years. Okay. Okay, so if it is capable or not, it only depends on it's less or larger than number 1. So if it's 1.33 is larger than number 1, it should be capable. Okay. So just give. So this is what we have for the process capability. Now let's take a look with an example. This is just give you the interpretation larger, equal, or less than 1. So let's take a look with these examples here. Suppose that design engineering team set the specifications for length of a stapled sheet metal part at 10 inches. And the tolerance is plus minus 0.05. The average length is the 9.99 and the standard deviation is 0.015. So how to find CP? CP equal to absolute value, the USL minus LSL divided by 6 sigma. So what is upper specification limits? How to find that? Do we have the upper specification limits directly here for the problem information? Give me some feedback. You're so silent. Okay. Yeah, go ahead.
Yeah, we would just take the specification length of 10 inches. For the upper limit, you'd add 0.5 inches to it.
Yes, great. Thank you, Matthew. And reminds me, next Wednesday, I own you a sticker. Okay. So so the upper limits here, it equals to the target value, which is you design 10. So we have 10 plus the tolerance, while the lower limit is the 10 minus 0.05. So this is how we find this. Now what is sigma? So sigma is 9.99 or 0.015. Which one? Which number here represents the sigma? Five 5.015, 1, 9.99, 2. Okay. Okay. So let's unpause here. The 9.99 is what we call the actual stepping process. So this is like your target is 10. But once you connect all the information, you find the average actual is 9.99. So 9.99 is the actual average of the data you connect. It's not the sigma. Sigma is the standard deviation. So the standard deviation is 0.015. And when you compute the CP, you should be very careful to find the right numbers with using the formulas here. So based on what we have over there, then we will be able to, okay, CP equals to upper limits minus lower limits divided by 6 times standard deviation, then we have 1.11. Now again, so it is capable or not capable? Great. So all of you feel like it's capable. Yes, it's capable because it's larger than number 1. So it's capable. Okay. So let's end the poll here. And this is what we learned for today's class, like the CP. And next class on Wednesday, we will continue learning like the CPK. But the end of today's class, let's do a practice together. So for this problem, you don't have to compute the CPK, but only focus on the CP. So what is the CP? And I gave you like around 3 to 5 minutes, and then let's talk about that together. And the first person who inserts your result in the chat box, you earn the sticker. Okay, okay. I have already like all the answers here. Okay, so Matthew, Mason, and Brittany, you will earn the sticker, okay? And I gave you like 1 more minute or maybe 2 more minutes to wait for other students to figure that out. Then let's talk about that together. Let me take a picture. Okay, let's talk about this. So for the CP, we need to find the upper and lower specification limits, and we need to find the standard deviation. And the lower and upper specification limits we can find for the target and the tolerance. So we will know the upper limits equal to A plus 0.6, which is 8.6. And the lower limit is A minus 0.6, which is 7.4. And then we will be able to find Cp equals to the upper limits minus the lower limits and divide it by 6 sigma. So 6 times sigma. So the sigma we find is the standard deviation here, which is 0.192. And then we got 1.2 divided by 1.152. So we got 1.04. So 1.04 is the result, but what kind of conclusions you get? It is capable or not capable? Let me pull the again. Okay. This process is capable or not? Okay. Can I get the reason like why you choose no or why you choose yes? So I found one of you like choose no. Okay, so if we're back to here, 1.04, if we only consider like compare with number 1, then yes, above 1 is capable. Yes, exactly. But if we back to the problem information here, the target process capability ratio is 1.33. So except for you say, okay, the process is capable, you also need to mention that it's not meet the target because the target is over 1.33. It's kind of a higher standard. Even like 1 means, okay, it's great, the process is good to go. But if you have a higher, like you want to reduce the variation, like even this is like, for example, so this is the distribution and they are within the limits, so it's capable, your process is good. But what if, like this is the limits, but you have a higher standard? Oh, you didn't mean technique now. Okay, that's great. So it will be over there, the variation reduced. It means like 1.33. So if we back to this problem, like even it's capable, but you also need to mention that it doesn't meet your target of the in terms of the process capability. Okay, so this is what I'd like to introduce for you for today. I just like forgot to record this lecture at the beginning, but sometime after like 5 to 10 minutes, I start to record these videos and I will post these videos in Canvas as well. And we don't have class next Monday because I will go to attend a conference and see you on next Wednesday. Okay, any questions for today? And it's so cold outside, so stay warm and I hope you have a wonderful weekend. Okay, any questions? You good? Okay, then see you next Wednesday. Have a wonderful weekend. Stay warm.
Thank you.
Thank you. Bye bye.